Good evening, everyone. A warm welcome to all of you in the sixth talk of STEM's Qualifier Camp 2021. Today, we have Professor Srikanth Srinivasan with us. He is an assistant professor in the Department of Mathematics at IIT Bombay and currently at the Department of Computer Science at Aarhus University. Let me give you a brief introduction about him. He completed his PhD from the Institute of Mathematical Sciences in 2010 under Professor V. Arvind. He was also a member in the Computer Science and Discrete Mathematics group at Institute for Advanced Study, Princeton, from 2010 to 2011. He did his postdoc at Center for Discrete Mathematics and Theoretical Computer Science, Rutgers University, from 2011 to 2012. His interests are mainly in the computational complexity theory. Today, he will be delivering a nice talk and a very beautiful and showing the interesting connection between how solvability and non-solvability of polynomials, polynomial equations have led to many new discoveries in various fields of mathematics, and also their interesting consequences in combinatorics and also automated theory. I hope all of you enjoyed our talk. Over to you, Professor.
Okay, so I guess I'm audible, right, Amik?
Yes, sir, you are audible.
Okay, great, perfect. So yeah, thanks very much, Amik, for the very kind introduction, and thanks for inviting me to give this talk. So very happy to be giving this talk at this event, if not in person, at least digitally. Okay, so let me start with kind of a brief introduction to the subject matter of this talk, which is about polynomials. Okay, so what are polynomials? So it's something that we all sort of study about in school, right? So polynomials, probably the first time you take an algebra class, you have questions about solving quadratic polynomials. Okay, so you have some sort of quadratic polynomial equation, maybe given by a polynomial like this, equal to 0. And you know how to do various things with this polynomial. You know, for example, how to draw the curve of the graph defined by this polynomial. So that's going to be some sort of curve in the xy plane. You know how to draw this curve. You know how to find the roots of this polynomial, which is essentially finding the points on the x-axis where this curve intersects the x-axis. Okay, and you know various things about quadratic equations. Okay, but mostly when we study about polynomials in school, we're talking about polynomials in a single variable. Okay, so in this case, there's just a single variable x, and we're looking at degree 2 polynomials in x. So the highest exponent of x is 2. So it's a degree 2 polynomial. Okay, but in this talk, we are not going to sort of restrict ourselves to just degree 2 polynomials, or in fact, even just a single variable. We're going to look at polynomials in many variables. Okay, so for example, you can look at polynomials in 2 variables, x, y. So here's a nice such polynomial, x squared plus y squared. So once you go to 2 variables, graphing the polynomial sort of is not so easy anymore. You have to look at a 3-dimensional space in which to graph this. So if you graph, for example, this particular polynomial, of course, it's not a curve, it's something like a surface. So you get this kind of cup-like geometric object. And this is an example of a quadratic. So it's still degree 2, so it's a quadratic, but bivariate polynomial because it depends on 2 variables. Okay, but there's no reason to stop here. We can look at polynomials in many variables. So here's a polynomial that some of you maybe who are in 10th standard and above may have seen. So this is something called the determinant. Okay, so whenever you have a square matrix, you can take what is called the determinant of the matrix. So if you don't know what it is, not really important. It'll show up a little bit later on in the talk, and I'll tell you a little bit more about it. But for those of you who have seen it, the determinant you can think of as a polynomial in the entries of the matrix. Okay, so if each entry of this 3 by 3 matrix is thought of as a distinct variable, the determinant is actually a polynomial in these variables. If you write it out, it looks something like this. Okay, so you can see here it's a degree 3 polynomial because I'm multiplying 3 variables at a time, and it's a polynomial in 9 variables. Okay, so it's a degree 3 polynomial in 9 variables. Okay, so it's no longer so easy to sort of draw or visualize this polynomial kind of geometrically. But still, you can ask many interesting questions about such polynomials, and answers to these questions lead to very nice applications in computer science and mathematics, number theory, many things. Okay, and so this is what the subject matter of this talk is. All right, so before I sort of begin with some technical stuff, I just want to do a little bit of a history lesson. Okay, so the history of the study of polynomials is almost as old as mathematics itself. Okay, so people have been, as long as people have been doing mathematics, they've been solving polynomial equations of various kinds. So for example, the simplest case of solving polynomial equations is the case of solving linear equations, degree 1 equations. Okay, and way back in the more than 2000 years ago in China, they were already studying the question of solving linear equations in many variables. So maybe you have 3 or 4 variables and you have a bunch of linear equations in these variables. How do you solve them for a solution? Okay, and this problem was already studied in China back in the quite some time ago. Okay, and in doing so, they actually discovered a method that we still use today to solve linear equations in many variables. And this method is called Gaussian elimination. Okay, Gaussian elimination is actually named after a famous German mathematician Gauss from the 19th century. But in some form, this method was already known to the Chinese mathematicians over 2000 years ago. Okay, so it's a very old history. Coming to non-linear equations, to quadratic equations, for example, mathematicians 4,000 years ago in Babylon were already looking at how to solve quadratic equations in a single variable. Okay, so back in 4,000 years ago, Babylonian mathematicians were already considering this problem and they gave some sort of solution for it. Okay, but it was not like a complete solution, not the kind of solutions we know today. For instance, Babylonian mathematicians didn't think about negative numbers. So for them, negative solutions didn't exist. Okay, and about 2000 years ago, a famous Greek mathematician named Euclid started making connections between solving quadratic equations and conic sections. Okay, so some sort of geometric connections between solving equations and geometry. And sometime later, the famous Indian mathematician Brahmagupta actually came up with a general formula for solving quadratic equations. Okay, that we all learn about in school these days by completing the square. So that's something that Brahmagupta came up with, and he was I think he started admitting negative solutions. So that was a step forward in that respect. Okay, so quite a bit was known about solving quadratic equations quite early in mathematical history. But when it came to higher degree equations, cubic or quartic equations, such solutions were not known for a long time. And it was only in the 1500s that some Italian mathematicians were actually able to solve general cubic and quartic equations. Okay, so in 1500s, they found like general formulas for solving cubic and quartic equations, but still in a single variable. Right. So progress, you can see, was kind of slow and stuttering. But in the 1600s, progress really took off. And the reason for this is that Fermat and Descartes, they sort of generalized the observations of Euclid and saw that many different geometric questions could be recast in the language of polynomials and algebra. Okay, and this allowed a whole host of new questions to be tackled with algebraic techniques. And this in turn led to a lot of development in the study of solving polynomial equations. Okay, so from here is where the study really took off. And pretty soon after, this connection led to many new fields of mathematics devoted to understanding polynomials and their solutions. Okay, these fields include things like Galois theory and group theory, to algebraic geometry, which is more or less the study of this connection between geometry and algebra. Fields like number theory were greatly benefited from this kind of understanding of solving polynomial equations. Okay, so many fields of mathematics were born and greatly benefited from this understanding of polynomials and how to solve polynomial equations. Okay, in the 20th century, this kind of development continued, but now there were more new fields of mathematics. So with the advent of computers and computer science, the theory of computation, which is purely a mathematical field, that also sort of took over. And here again, there were applications of polynomials and algebra. And in turn, these motivated new questions in polynomials and algebra. And similarly in combinatorics, which is study of discrete objects of various kinds, again, there was this a bunch of applications of polynomials and new questions about polynomials. Okay, so this is sort of a brief history of the study of polynomials and its importance in mathematics. And what I'm going to mostly talk about is these latter applications to combinatorics and the theory of computation, principally the theory of computation to begin with. Okay. All right, so that's sort of a short intro to what we'll be doing. And now let's get into some slightly more mathematical stuff. Okay, so the question that I'll mostly be addressing about polynomials in this talk is a very simple one. It's something that you've probably thought about when you learned about polynomials in school. And the question is, how many roots can a polynomial have? Okay, so for example, when we are thinking about solving a quadratic polynomial, maybe it's something like ax squared plus bx plus c, the first question to ask is, okay, when I'm solving it, what does that mean? I'm trying to find the roots. I'm trying to find the points where p of x is equal to 0. Okay, and the first question is, how many such points can be there? How many x can there be of this nature? Right? And so you've probably learned from the quadratic formula in school that there can be at most 2 such roots, right? So if you plot the graph of this polynomial, this graph can either stay completely above the x-axis, in which case there are no roots. It can intersect the x-axis, can just briefly touch the x-axis, be tangent to the x-axis, in which case you get a single root, or it can go below the x-axis like this, in which case you get 2 roots. Okay, so you can have up 0, 1, or 2 roots. Okay, so that's the situation for a quadratic polynomial. But there's one important exception, right? So there's one exception to this rule. And that exception is when all these 3 numbers, a, b, and c, are 0. Okay, and when all these 3 numbers, a, b, and c, are 0, then it's not really a quadratic polynomial, it's the 0 polynomial, right? It's just always 0. And the 0 polynomial doesn't have 0, 1, or 2 roots, it has infinitely many roots. Every point is a root. Okay. So with the exception of the trivial 0 polynomial, all non-zero quadratic polynomials have either 0, 1, or 2 roots. Okay, so this is something that we kind of implicitly learn in school. Okay, and the great thing about this is that it generalizes to not just quadratic polynomials, but higher degrees as well. Okay, right, so this is an example of a quadratic polynomial with 2 roots. So for any 2 points alpha, beta, I can look at the polynomial x minus alpha into x minus beta. That's a polynomial 2 roots. And this observation that a quadratic has at most 2 roots generalizes to higher degrees. What does that mean? Well, if I take a cubic polynomial, right? So now I'm allowing degrees up to 3. Then a cubic polynomial can have up to 3 roots. Okay, so it can have up to 3 roots. Okay, and again, there's this proviso that it should be a non-zero cubic polynomial. If all these 4 coefficients a, b, c, d are all 0, then the cubic will have infinitely many roots. But assuming that it's a non-zero cubic, it has up to 3 roots. All right, and so this is not something that you see so much in school unless you've thought about cubics a little bit. So, but it's very easy to see why this is true. So why is this true? Let's just quickly see. So for example, if I have some number alpha as a root of this p of x, then I can write p of x as x minus alpha into something else. Okay, that's what it means for p of alpha to be 0. P of x is x minus alpha into something else. Okay, and now p is a degree 3 polynomial. It's a cubic polynomial. X minus alpha is a degree 1 polynomial. So what's left over here is a degree 2 polynomial, right? And so therefore, the roots of p are alpha and the roots of q. Okay, so that's 1 plus 2, which is at most 3. Okay, so any cubic can have at most 3 roots. This sort of proves it. And there's no reason to stop at 3 here. You can go to any number you want. Okay. So by mathematical induction, for example, you can show that any non-zero degree d polynomial has at most d roots. Okay, and the proof is exactly the same. Every time you find a root, you will be able to find a factor of this polynomial of this form. You can divide out by that factor, and what's left is one lower degree, and you continue this process until you have no roots left. Okay, so any non-zero degree d polynomial has at most d roots. Okay, and this is a kind of a straightforward mathematical fact. And again, this is actually, it can happen that a degree d polynomial has d roots. So for example, you can take this polynomial x into x minus 1 into x minus 2 and so on until x minus d minus 1. This is a degree d polynomial with exactly d roots. Okay, so every non-zero degree d polynomial has at most d roots. Okay, so this is a very nice simple fact about univariate polynomials. And already this very, very simple fact has some very nice applications to engineering, specifically electrical engineering and computer science. Okay, so I want to tell you a nice application of this. Okay, and so this application is to something called coding theory. Okay, so what does this mean? So suppose there are 2 people, and it's typical in coding theory to call them Alice and Bob. Okay, so you have 2 people, Alice and Bob, who are sitting very, very far from each other. Okay, so as an example, you can think that Alice is an astronaut on the International Space Station, for example, and Bob is a scientist, maybe in ISRO or in NASA or whatever, sitting somewhere on Earth. Okay, and now Alice wants to send a message to Bob. They want to have some sort of communication between each other. Okay, so Alice has a message M that she would like to transmit to Bob. right? So Alice and Bob are sitting very far away from each other. So they're using some sort of means of communication, maybe some sort of radio waves or some sort of waves of that form, right? And so now when Alice sends her message, she's sending it across a channel through which the radio waves are transmitted. And by its very nature, any channel tends to corrupt a message that passes through it, right? So whatever energy that's passing through it is going to be corrupted by the channel in some way. So Bob receives a message, maybe M dash, which need not be the same as the message N. Okay, so receives a kind of corrupted version of the message, right? And this poses a challenge to Alice and Bob, because Alice would like to communicate reliably with Bob. She would like to tell Bob exactly what she means, but at the same time, the channel is going to corrupt the message, and that's going to make it hard for Bob to be able to tell exactly what Alice said. Okay, and this can cause real problems in like mission critical applications. So for example, Alice might be an astronaut, as I said, and she might want to go out on a spacewalk, on the International Space Station to maybe fix something, right? This requires perfect coordination between her and the scientists on the ground. And maybe Alice wants to say, we are not ready. So we are not yet ready to do the spacewalk. Okay, and but the channel corrupts this message, and what Bob hears is we are now ready to do the spacewalk. Okay, so this is not the kind of miscommunication you want in such a situation, right? So what happens in general is that human language is not set up in order to be able to handle these kinds of corruptions. You have sentences, for example, that are very close to each other, but have dramatically different meanings, right? So you don't want Alice and Bob to sort of have this kind of confusion between each other. Okay, so how would they sort of manage under this confusion? How would they kind of eliminate this kind of confusion? Well, the solution that Alice and Bob sort of come up with beforehand is to kind of encode their messages. Okay, so what they want to do is, instead of Alice her sending this message as is, she will encode the message in some way. And the aim of this encoding is to ensure that different messages, for example, these two different messages would have vastly different encodings. Okay, so when they actually send the messages, they look very, very different. So even if the channel produces a few corruptions in the message, Alice and Bob are still able to tell the difference. Okay, so Bob is not going to think that this message is equal to this message. Okay, so this is basically the solution. Okay, and yeah, I should say that this nice example is from from a talk that I heard by a famous Indian coding theorist named Madhusudan. And if you want to learn more about this topic, about how to encode messages this way, I would encourage you to go and look at his lectures online, which are very, very informative about it. Okay, so back to the setup. So what Alice and Bob want to do is they want to encode their messages in order to ensure that this kind of confusion is impossible. Okay, and the science of doing this is sort of called coding theory. So when some people hear coding theory, what comes into their mind is something like cryptography, where they don't want somebody to be able to eavesdrop and be able to find out what they're talking about. That is not the subject matter here. Here, what we want Alice and Bob to be able to do is to sort of reliably communicate whatever they want to say to one another, and not be confused by the corruptions induced by the channel in between. Okay, so that's the setup. All right, so how are they going to do this? And more importantly, in doing this, what is the connection between this and polynomials? Okay, so let me try to make that connection in the next slide. Okay, so let's go back to this fact about polynomials we saw a couple of slides ago. So we said that any non-zero polynomial of degree d has at most d roots. Okay, so any non-zero polynomial of degree, I said degree d there, but the same thing holds for degree at most d, because the degree is less than d, then there'll be even fewer than d roots. So any non-zero polynomial of degree at most d has at most d roots. Okay, so this is what we saw some time ago. Okay, so let's just write this fact in a slightly different way to see why it's useful. Okay, so suppose I have two distinct polynomials, p of x and q of x. They're both of degree at most d. Okay, then if I look at their difference, right, p of x minus q of x, it's the difference between two distinct polynomials of degree at most d. So that's going to be a non-zero polynomial of degree at most d, right? R is going to be non-zero because these two are distinct. And therefore, R has at most d roots, right? That's what the first sentence says. Okay, so but what does that mean about P and Q? Well, R is 0 exactly when P and Q agree on X, right? R of X is 0 exactly when P of X is equal to Q of X. So it's 0 exactly when P and Q agree on X. So what this means is that any two distinct degree d polynomials, so any two distinct degree d polynomials can agree on at most d points, right? Because every time P of X and Q of X agree on a point, which is to say P of X is equal to Q of X, every time that happens, then R of X is 0. But R has at most D roots, so they can agree on at most D points. Okay, so there's a pretty simple, it's just a simple way of rewriting what we saw above. But what does this mean, right? So just think about it. Imagine that I have P on a large number. I have P of X for many, many different values of X. I have Q of X for many, many different values of X. And what this fact is telling me is that P of X and Q of X can agree on at most D points. So that means these two different polynomials, they're only of at most D points on which they can be the same. These two sets of values can be the same. And therefore, distinct polynomials in some sense are far apart from each other, right? Because they can agree on very few points, right? And you should really think of this as analogous to what we're trying to do with messages in coding theory. In coding theory, what we're trying to do is we're trying to ensure that different messages, their encodings are far apart. And here we already know that distinct polynomials in some sense are far apart. And now we just have to be able to apply this in a coding theory scenario. Okay. All right, so how do we do this? So let's get back to the coding theory problem and see how polynomials are applied. Okay, so suppose Alice has this message that she would like to send. So Alice has, we are not ready. She wants to send this across to Bob. And let's say Alice and Bob decide beforehand that every message that Alice sends will have at most maybe 20 characters. Okay, so she's going to send messages, but maybe every minute she sends a message, which is at most 20 characters in length. Okay, so we are not ready is slightly less than 20 characters. So maybe she can add some spaces at the end to make it exactly 20 characters. Okay, so now what is Alice going to do with this message? Well, the first thing she's going to do is treat this message as a sequence of numbers instead of as a sequence of characters. Okay, so how does Alice do that? Well, there are many ways of doing this, but for example, she could do this. This is a very silly encoding where I've taken each alphabet from A to Z, and I'm treating it as a number from 1 to 26, and I'm treating the space as the number 0. Okay, so if you translate we are not ready into a sequence of numbers like this, so you'll get some sequence of numbers. Okay, and the sequence is a sequence of at most k numbers, maybe k equals 20, so it's a sequence of at most 20 numbers. Okay, so what Alice has done is translated her sequence of characters into a sequence of numbers. Okay, so how is she going to transmit this? Well, what she's going to do is she's going to translate, first she's going to make the sequence a polynomial. Okay, so how does she turn a sequence into a polynomial? Well, what is a polynomial, right? A polynomial is just a sequence of coefficients times powers of a variable. So for example, what Alice could do is she could come up with a degree k-1 polynomial where the coefficient of x bar 0 is the first element of the sequence, that's 23. The coefficient of x bar 1, sorry about that, is the second element of the sequence, that's 5. And the coefficient of x bar 2 is 0, and so on. Okay, so just by turning the elements of the sequence into the coefficients of her polynomial, she can turn the sequence into a polynomial. Okay, so Alice, what she's done so far is turn her sequence into a polynomial, but she's not actually going to send this polynomial per se, but she's going to evaluate this polynomial at a bunch of points. So her final message is just the evaluation of this polynomial at a bunch of points. So she's going to evaluate this polynomial at 0, 1, and so on until 2k. Okay, so that's just 2k plus 1 different values of the variable x. And for each value, she's going to evaluate the polynomial at that point x, and she's going to get a number. So this is another sequence of numbers. And what she's going to transmit is finally this sequence of numbers. Okay, all right, so that's the setup. So why is this useful? Yeah, well, just think about it. So suppose Alice, there were two distinct messages, maybe M1 and M2. Since there are two distinct messages, they will give rise to two distinct sequences of numbers. Okay, and as a result, will give rise to two distinct polynomials of degree less than k. Right? And what did we know already? We know that two distinct polynomials of degree less than k can have at most k roots. So what that means is that two distinct messages can agree at most k points. Right? And here, how many points is she sending? She's sending 2k distinct points. Okay, 2k plus 1 distinct points, right? Which means that any two distinct messages can agree on at most 50% of the points, right? So even if you started with two messages that were very, very close to each other, maybe they agreed on all except the first position. After this encoding, they end up disagreeing on at least 50% of the positions, Okay, so imagine Alice and Bob trying to communicate. Now, if there are two drastically messages which have drastically different meanings that look very similar to each other, after this encoding, they are going to differ on 50% of the points. And therefore, if Alice sends one of the messages, it's very unlikely that the channel will be able to corrupt it to another message. Right? Of course, it's possible if the channel corrupts almost everything to corrupt this message also to another message. But assuming that the channel is not introducing too many corruptions, one can easily see that distinct messages, it's unlikely for Bob to get confused between distinct messages that Alice sends. Okay, so this is kind of a beautiful application of polynomials to coding theory, and this kind of encoding is what is called as a Reed-Solomon code. So it's sort of a very well-studied error-correcting code in the field of coding theory. Okay, so is there any questions about this at this point, Amit? Are there any questions about that?
Currently, I don't think there are questions.
Okay, all right, good. Yeah, so at any point, yeah, if I should have said this right at the beginning, at any point, if you find something confusing, feel free to send in a question to Amit and he'll let me know.
Yes, yes.
Sir, if there is corruption only at the main part, like corruption is at NOT only, then how we know that it is less than 50%?
Sorry, can you say that corruption where?
Corruption is only in the main part of the message. Like here, the main part is NOT and ready.
So right. So the corruption could be anywhere, but the final message that is sent, if you note, see this NOT is not actually sent at all, right? This NOT is translated into some coefficients of the polynomial, and then we evaluate the polynomial at various points and we send it. So in some sense, NOT is never sent across the channel. What is sent across the channel is the evaluation of the polynomial at all these points. So this is the final message that actually gets transmitted across the channel. So one way of saying it is that this NOT, whatever information is there in NOT, is actually spread across all the points of the message. Okay, in some sense, it's sort of distributed through all the points of the message. So the only way to introduce corruption only in NOT is to sort of introduce corruptions in every little point of the message, which is unlikely. Okay. Does that make sense?
Yes, sir.
Okay. Any other questions about this?
Sir, can I ask?
Yes, please.
If all these PM of 0, PM of 1, all of them, if assuming there is no corruption, we could just take any one of them and get the message back. Is that true?
So that's a very, very good question. No, unfortunately, you cannot take any one of them and get it back. And but you can take any k of them and get it back. Okay, so it's essentially related to the fact that if you want to find out what a degree k polynomial is, or degree k minus 1 polynomial is, you need its evaluations at any k points, right? So you can just imagine, like, if you have a linear polynomial, which is just a line. If I tell you the value of a linear polynomial at 2 points, you can recover it. But if I tell you the value at just 1 point, you will not be able to recover the line. Okay, it's related to that, but it's a very, very good question.
So is this polynomial encoding means encoding the whole message into a polynomial by the transmitter?
Yes. So this will be part of your hardware. So you will enter the message, and the hardware will turn this into polynomial encoding, and that's what it will be transmitted. Yes. Okay, great. So all good questions. Yeah, feel free to ask more. So this is sort of a very, very simple application of essentially basic high school algebra in real world applications of coding theory. Okay, so this is sort of just the surface of this whole area. So even when you just look at Reed-Solomon codes, these polynomial-based codes, you can also ask about other questions. So for example, if there are a few corruptions, Bob will be able to tell that there are a few corruptions, but there's still the problem of being able to recover the original message in the presence of corruptions. Okay, so this is related to a question that was asked. What was asked some time back is, what happens if there are no corruptions? Can you recover the message? But you can also ask, if there are a few corruptions, can you recover the message? And it turns out you can. Even up to 50% of corruptions, you can handle and recover the message. Yeah, and in fact, there is an extreme version of this. Even if the channel introduces 99% of corruption. So 99% of your message is corrupted. So most of your message is corrupted. Just 1% of your message is sort of uncorrupted. You can still recover some considerable amount of information about the original message from just this information. Okay, so there's a lot more behind this, and these are considerably more advanced ways of doing this. So the first one was an algorithm for doing this, was discovered in the 60s, and this last one was only done in the 90s. Okay, so already you can see that starting with very simple questions about polynomials, you start kind of extending these ideas a little bit more. You get very close to current research about polynomials. Okay. All right, so that's all I had to say about Reed-Solomon codes. So let me go on now to a slightly different application, again to do with polynomial roots. Okay, so we saw some time ago about how many roots a univariate polynomial of degree at most d can have. Okay, so now in order to kind of motivate my next application, I want to ask how many roots a multivariate polynomial can have. Okay, so I want to understand the answer to this question: how many roots can a multivariate polynomial have? Okay, and now, so if you think about this question for a while, you realize that even in the setting of just two variables, let's say x and y, in the setting of two variables, you have to ask this question in a kind of a delicate, in a suitable way. Otherwise, the answer is not very reasonable. Okay, so let me just describe why that is. So let's take this very simple polynomial, for example. So let's take the polynomial x squared plus y squared minus 1. Okay, so this is a simple quadratic polynomial in two variables, right? And we all know that the roots of this polynomial correspond exactly to the points of the circle in the xy plane. Okay, so how many roots does this polynomial have? Well, the roots of this polynomial are the number of roots. The number of roots of this polynomial is equal to the number of points in the circle. So that's infinitely many roots. Okay, so that's more or less an answer to a question. Even a degree 2 polynomial in two variables can have infinitely many roots. Okay, right. But this is not quite the end of the road here. You can still sort of try to refine this question. Okay, so if you look at this picture here, sort of something that strikes you, that should strike you, is that the plane, the xy plane, is a kind of a much bigger set than the set of roots of the circle, the set of points in the circle. Okay, so though this polynomial has infinitely many roots, while seen as a fraction of all the points in the xy plane, this is still a vanishingly small fraction. So there's very, very few points in the plane that are actually on the circle. Okay, so and the reason for this is that the set of points in the circle is sort of formed like a one-dimensional set, right? So this is sort of like a one-dimensional set inside a two-dimensional plane. So this is actually very few roots in some sets. Okay, and we can try to make this precise in various ways. So for example, mathematicians have tried to make this precise by counting different orders of infinity. Okay, and this can be done in multiple ways, and in some sense you can say that the polynomial has few roots. But another much simpler way, sort of very, very useful way, is to just count the set of roots of the polynomials not in the whole plane, but just in a finite subset of the plane. Okay, so we're not going to look at all the roots of this polynomial, but we're just going to look at the roots of this polynomial that lie in some finite subset. Okay, and that will also already be very, very useful for us. So what we'll do is that we're going to count the number of roots that this polynomial can have in a kind of a finite two-dimensional subset, and we'll be able to say that any degree 2 polynomial in two variables, non-zero degree 2 polynomial, will have few roots in this finite two-dimensional set. Okay, and that will be useful. So let me describe how this is done and how to apply this to some other questions. So what's this two-dimensional set that we'll be looking at? Okay, so it's a very simple set. So if I ask you to come up with a two-dimensional finite set, this is probably the first one you'd come up with. So this is just going to be the n by n grid. Okay, so just take all integer points in the plane. So these are points where both the x and y coordinates are integers, and they take values between 0 and n minus 1. Okay, so I'm just looking at this square here, this n by n square, and let's look at all the integer points inside the square. Okay, so I'll call this the grid Gn. Okay, so it's just the n by n grid. Okay, and the question now is, how many roots can a non-zero quadratic polynomial have in this n by n grid? Okay, how many roots can it have? Yeah. Now it will never be the case that a polynomial has infinitely many roots, because I'm only looking at a finite set of points. Okay, but nevertheless, looking inside this finite set of points already sheds a little bit of information about this polynomial. Okay, all right, so this is the question. So how many roots can a non-zero quadratic polynomial have in this grade? Okay, and before we answer this question, let's look at a simple example. Okay, so here's this example. So this is kind of a polynomial in x and y, but it's a kind of a silly polynomial. This polynomial does not involve the variable y at all. So it completely ignores the variable y. So it's just the polynomial x times x minus 1. Okay, so polynomial x times x minus 1. It's a polynomial in just the variable x, but I can think of it as a polynomial in two variables also. I can think of it as a polynomial in x and y. It's just that it does not depend on y at all. Okay, so how many roots does this polynomial have in this grade? Okay, so let's see. Well, for this polynomial to vanish, either x has to be 0 or x has to be 1, right? But now when x is 0, that sort of corresponds to the y-axis here, right? I'm setting x equals 0, so I'm going to get the y-axis. And along the y-axis, the grid has n points, okay? So that gives me n roots just because x is 0. Okay, and similarly, if I set x equals 1, that sort of corresponds to the vertical line just next to the y-axis, right? And again, there I will get n points. Okay, so overall, I'm going to get n roots from setting x equals 0 and n roots from setting x equals 1. So I get overall 2n roots. Okay, all right. So here's an example of a non-zero degree 2 polynomial, which has 2n roots in the grid. Okay. And you should think of this capital N as being quite large, let's say 10,000 or something. So you have a single degree 2 polynomial which has 20,000 roots in this grid. So that's a lot of roots. But at the same time, if you look at the total number of points in this grid, that's n squared. Okay, and that's going to be much, much larger than 2 times n. Okay, so the polynomial has lots of roots, but it's a much, much smaller, it's a very small fraction of the grid. Okay, so you have a non-zero quadratic which has, in comparison to the size of the grid, few roots. Okay, and this example sort of illustrates a general fact. Okay, so there's a general theorem that says that any non-zero quadratic polynomial p of xy, so here p doesn't have to be the polynomial on the previous slide, but can be any non-zero quadratic polynomial, it has at most 2n roots in this n by n grid. Okay, so compared to the size of the grid, it has very few roots. All right, and actually I want to tell you a proof of this. This is probably the only proof I'll be doing in my talk, but it's a pretty simple one, so I thought I'd go through it. So let's go through this proof. Okay,
is it p2 x comma y, or is it in any n tuple? Is it valid for 2 variable or any several variable? This theorem is valid for.
So it's a very good question. So I'll just get to that on the next slide. But yeah, the short answer is there is some form of this theorem for any number of variables. Okay, but I'll tell you exactly the form of this theorem that is true on the next slide.
Okay, thank you, sir.
All right. Okay, so yeah, so let's just quickly go through the proof of this thing. So suppose P is some non-zero polynomial. Okay, so what the proof is going to look like is it's going to look at the structure of P, and there'll be a slightly different argument based on the structure of P being different things. Okay, so the easiest case is when the P is like a polynomial on the last slide. So let's say it's a polynomial in just the x variable, completely ignores the y variable. Okay, so that's just a quadratic in x, right? Ax squared plus bx plus c. And what do we know about quadratics in a single variable? They can have at most 2 roots. That's something we already know, right? And every time this polynomial vanishes, so maybe it vanishes at x equals 1, that gives me n roots in the grid, right? Because y can still take values from 0 to n minus 1. So every time a polynomial p of xy vanishes for some value of x, I get n roots in the grid, right? But it can vanish for at most 2 values of x. So overall, I get at most 2n roots in the grid. Okay, so for this kind of polynomial, the analysis is exactly like what we saw on the previous slide. At most 2 roots for x in x, and each of those give at most n roots in the grid, so at most 2n roots.
So px comma y is a quadratic polynomial.
It's a quadratic polynomial, exactly.
Thank you, sir.
Yeah. Okay. All right. So let's moving on. So not every quadratic polynomial needs to look like this, right? In general, a quadratic polynomial here will involve both x and y, right? And it can involve terms in y of degree up to 2. That's what a quadratic polynomial is. Okay, so the next case, let's look at a case where the polynomial actually involves the variable y. And in fact, the simplest case there is when, let's say, it involves the variable y with degree 2. So it actually has y squared as one of the terms. Okay, so let's look at such a polynomial. So this polynomial has y squared, maybe with some non-zero coefficient a. And then it has many other terms, right? It might have terms like xy, it might have terms like y, x squared, etc., etc. So all those terms, let's put them together in a single polynomial that I'll call q of xy. Okay, so this is the term involving y square. This is all the other terms. Okay, now how many roots can p of xy have in the grid? Okay, so let's see. So what I'm going to do is, instead of looking at the whole grid, I'm going to just divide the grid into vertical lines. Okay, and I look at each vertical line separately. Okay, so suppose I'm looking at the vertical line corresponding to x equals alpha. This is this vertical line here. So I want to know how many roots can be there on this vertical line x equals alpha, right? So what does that mean? That means that I'm going to substitute x equals alpha in this polynomial, right? I'm going to just look at p of alpha y. I'll just substitute x equals alpha. And now what I'm left with is a non-zero quadratic polynomial in y, right? And why is this? So we just have to be a little bit careful here to ensure that this is a non-zero quadratic. Well, the degree is at most 2, because in the beginning, the degree was at most 2. The degree cannot increase. So the degree is at most 2. So it's a quadratic polynomial. But why is it non-zero? The reason it's non-zero is that y squared has a non-zero coefficient, and that's not going to be disturbed by substituting x equals alpha. Okay, so it remains like a non-zero quadratic polynomial. Okay, and now we know that any non-zero quadratic polynomial has at most 2 roots. That's just a univariate case now. So along each vertical line like this polynomial has at most 2 roots. Since there are n vertical lines overall, you get at most 2n roots. Okay, so again, in this case, we get at most 2n roots. Okay, so, and there's one final case. The final case is if the polynomial involves y, but doesn't involve y with degree 2. Okay, so it involves y only with degree 1. Okay, what does that mean? Well, if it involves y only with degree 1, that means that the polynomial will look something like this. So suppose I take all the terms involving y together, they look like this.
Sir,
right?
but same proof can follow up there as well, right?
Sorry, please go ahead.
I think you can use the same proof there as well.
You're absolutely right. We can use the same proof.
But
there is
you
just
can
one.
compare the horizontal lines instead.
Oh, I see. No, but even if you take the horizontal lines, it may involve it may not involve x squared. So you may have just degree 1 in both x and y. So in which case the previous proof will not be applicable exactly as is, but there's a small modification that I'll talk about on this slide that will be applicable. But you're right, it's almost the same. Okay. So let me go through it. So let's say, so it involves p with degree 1 in y. So now the coefficient of y looks something like this. Okay. And now again, we do the same thing. So we divide the grid into vertical lines. And let's say I take a particular line corresponding to x equals alpha. Okay. So again, I'll substitute x equals alpha in this polynomial. And if this coefficient of y it become a alpha plus b, if that coefficient is non-zero, then I have a linear polynomial in y, right? A linear polynomial in y, it's a univariate polynomial, so it can have at most 1 root, right? And since there are n vertical lines, if I have 1 root per vertical line, I get at most n roots. So that's the same. But one small hiccup can take place is that for some values of x, this entire coefficient can vanish, right? This a alpha plus b, of course, can be 0. And when a alpha plus b equals 0, it's not clear that the polynomial, what happens to the polynomial. In the worst case, the entire polynomial can vanish. Okay, so for example, this q of x might not have anything. So in which case the whole polynomial could vanish. Okay, so we just have to be a little careful about handling that case. So when a alpha plus b equals 0, the entire polynomial vanishes. And when the entire polynomial vanishes, all the points on the grid, all the points on this vertical line become roots. Okay, so you get n roots from these vertical lines. But the important observation is that this can happen for at most 1 alpha, right? Because ax plus b is a linear polynomial in x. A linear polynomial in x can vanish for at most 1 value of x. So there's most 1 such alpha. So again, this gives at most n roots. Okay, so this is a kind of a slight case analysis based on whether this coefficient vanishes or not. If it does not vanish, you get at most n roots. If it vanishes, you get at most n roots. So overall, you get at most 2n roots.
Sir, I didn't get how to choose that alpha.
So it's not a matter of choosing alpha. You are going to run over all alpha going from 0 to n minus 1. Okay, and there'll be some alphas for which this, for most alphas, this a alpha plus b will be non-zero. And when it's non-zero on all those vertical lines, you'll get at most 1 root. Okay, but there may be one bad alpha for which this thing vanishes. And for that one bad alpha, you will get n roots overall on that line. Okay,
sir,
so that's why you get n plus n at most 2n roots. Okay, so
What about the q of x at that alpha on which ax plus b is 0?
Very good. Yeah, q might be 0 as well, right? So in the worst case, for example, so I have not assumed anything about q here, but maybe q is the 0 polynomial, in which case the entire polynomial could vanish. Okay. Okay, so great. So this is a kind of a short proof. I won't be doing too many more proofs like this. And actually, I'm not going to be using this proof for anything later on in the talk. But just to give you a flavor of the level of these arguments. So a very simple argument, and it's able to actually prove a pretty interesting fact, which is that any non-zero quadratic polynomial cannot vanish at too many points in this n by n grid. Okay. And the great thing about this proof is that there is nothing stopping us from changing this quadratic to higher degrees. Okay, so the same proof, more or less, I leave it as a nice exercise for you to check, is that the same proof more or less shows that a non-zero degree D polynomial has at most now, instead of 2 times n, the 2 now becomes D. So it becomes D times n many roots. Okay, in this n by n grid. Yeah, and again, there is a simple example that shows that there can actually be D times n many roots. If you again take this polynomial in just the x variable, where I take x into x minus 1 into x minus d minus 1, this polynomial actually has exactly D times n many roots. Okay, so any non-zero degree D polynomial has at most D times n many roots in the n by n grid. And finally, somebody was just asking this a few minutes ago, does this stop at 2 variables? And the answer is no. There is no reason to stop at 2 variables. If you do the same proof, only you add in induction on the number of variables, it works for any number of variables that you want. Okay. So if I'm working with 2, instead of 2 variables, I'm working with m variables. Okay, think of m as maybe 10 or 100. Okay. Now I'll no longer be working therefore with a 2-dimensional grid, but rather an m-dimensional grid. Okay, and now each variable still takes maybe capital N many values. So 0, 1 to n minus 1 for each variable. So now I have an m-dimensional discrete grid. Okay, and the theorem is that any non-zero degree D polynomial, okay, has at most, yeah, D times n to the m minus 1 many roots in this grid. Okay, D times n to the m minus 1. So let's just go back to a previous slide to compare it to the quadratic case. So that was m equals 2. And there we said D times n, right? Which is the same thing as saying D times n to the 2 minus 1. Okay. And now in general, for m variables, it's D times n to the m minus 1. Okay. So it's kind of generalizes the quadratic case very nicely. Okay. And so I don't want you to kind of get caught up in understanding this, getting very technical about this. But what I want you to think of this as saying is that at most points in the grid, the polynomial is non-zero. Okay, this minus 1 really makes a huge difference. So at most points of the grid, this polynomial actually takes non-zero values, and it vanishes at very, very few points in this overall grid. Okay, so that's sort of the take-home message. Okay, so again, this is also tight. Again, you can take the same polynomial that we've been looking at so far. You just take a polynomial in the first variable, x1, for example, and just take the polynomial x1 times x1 minus 1, and so on until x1 minus d minus 1. And this has exactly this many roots. Okay, all right, so what's the end result of all this? The end result is that we have sort of seen exactly how many roots a non-zero degree D polynomial can have in a discrete grid. Okay. So are there any kind of questions about the statement of this theorem? Anything that you would like to ask me before I go on to an application?
So are we dealing with only the integral roots of the polynomial?
No, we're not. Yes. So we are only looking at the roots that lie on the grid. So in some sense, we are dealing only with integral roots, right? We don't care about the roots that lie at other points. If we look at the overall number of roots, there'll always be infinitely many. So we only look at the roots in this discrete grid.
Can you change the grid like so that it can also include some real numbers? For example, you could consider some n by n grid, but it contains all the integral like multiples of, let's say, all integer coordinates with both coordinates even or something like that.
Yes, so there's nothing
we-
special about just taking 0, 1, 2 to n minus 1. You could take any set A cross B, right? So you could take any discrete grid. So it doesn't really matter. So for example, the points of discrete grid don't have to be integers. You can take, for example, multiples of pi on the x-axis and multiples of e on the y-axis. So it doesn't really matter what the grid, the individual elements of the x and y axis are. All that matters is that it's of the form A cross B, where A and B both have size n. Okay. Okay. Yeah. Okay, great. These are all great questions. So keep them coming. Okay, so fantastic. So we have now answered this question about roots of multivariate polynomials in a kind of a satisfactory way. And let me show you how it's useful. Okay, so just to say that this statement about polynomials has actually been discovered by many people over the years. Okay, so there's a mathematician, so this is probably known even earlier, but there was a mathematician in the 1920s named Ore who wrote this. Then there were other mathematicians in the 70s who were working in computer science related disciplines who all found this simultaneously, independently discovered this fact. Okay, and as a general rule in mathematics, you should remember that if something has been discovered independently by many different mathematicians doing different things, then that's a natural fact and worth remembering. Okay, so it's sort of a general rule in mathematics. It's something that's been found independently by many different people is probably a fact that is natural for some reasons. Okay, and this is such a fact. All right, so I want to use this and give it an application to computer science, okay, to an algorithmic problem called the perfect matching problem. All right, so what's this? So it's actually a very nice setup and it's quite useful in real world applications. So let me describe it carefully. So the setup is as follows. So suppose you have some n jobs. Okay, so you have some n tasks that need to be performed and you have n candidates. Okay, so n people who are who need to be asked to do these jobs. Okay, but sort of the time of these candidates is limited. So each candidate has time to do only one job. Okay, so the only way these n jobs are going to be done is if each candidate is assigned to a distinct job. Okay, so that's the general setup. Okay, but it's not just this much. You also have one more thing is that the candidates have certain preferences. Okay, not every candidate wants every job. Okay, so some jobs maybe are in the expertise of some candidates, and so they only want to do those kinds of jobs, and they're not interested in doing other jobs. Okay, so you have this additional layer of complexity on the problem. So you have n jobs, n candidates, but not every candidate wants to do every job. Okay, and the question is, can every job get done? That's the overall setup. Okay, and so let me just describe this example to you in this problem to you in a kind of pictorial way, which is very useful. Okay, so the picture is as follows. So on the left, I have 3 points. They correspond to, so in this case, I'm thinking of n equals 3. So in the left side, I have 3 points that correspond to 3 candidates, 1, 2, and 3. And on the right side, I have 3 points which correspond to 3 jobs, A, B, and C. Okay, and now I have put a line between a candidate and a job if the candidate is willing to do the job. Okay, so for example, candidate 1 is willing to do job B and C, but not willing to do job A. So I've only put lines between 1 and B and C. Candidate 2 is willing to do jobs A and B. Candidate 3 is only willing to do job C. Okay, so this is the setup. And now the question is, can you assign one job per candidate so that all the jobs get done? Okay, so is that possible? Well, in this example, you can see the answer is yes, right? Because the reason is that, so suppose you wanted to do this assignment, you can see that you have to give candidate 3 job C, right? Because candidate 3 only wants to do job C, so you have no choice but to give candidate 3 job C. Once you give candidate 3 job C, you can see that candidate 1 has only one option, which is to get job B. There's no other option. And finally, if you give candidate 1 job D, then candidate 2 has to get job A. Okay, So you can assign jobs to candidates in this way in order to ensure that all the jobs get done. Okay. And pictorially, this is sort of denoted like this, right? So I'm kind of, these are the lines that I'm sort of activating. So I'm saying that these candidates will do these jobs. Okay. And this kind of general problem is what's called the perfect matching problem in computer science. Okay. So in general, so let me describe this problem more generally. You're given this pictorial description is what is thought of as the general description of the problem. So you have two sets of points, which you can think of as n candidates and n jobs. Okay, these are also called vertices. You have a set of lines or edges. Okay, and these lines are supposed to indicate the preferences of the candidates for various jobs. Okay, and this entire pictorial structure that we saw on the previous slide, that's called a graph. Okay, or more specifically a bipartite graph, because it's coming in two parts, candidates and jobs. Okay, so you have a bipartite graph like this, and it's just jargon for that picture that we saw. And the general question is, does this graph have a perfect matching? Yeah, and what is a perfect matching? It's just a way of assigning each candidate a distinct job that's in there that they would like to do. Okay, not a job that they are not willing to do. Okay, so this is the general setup. Okay, so are there any questions about the definition of the statement of this problem?
Can you please explain the bipartite graph again?
Okay, so bipartite graph is just this kind of picture here. You have some vertices on the left, some points on the left, some points on the right, and some lines between them. That's all. That structure is called a bipartite graph.
All right, thanks.
Okay, so yeah, so maybe I'll do some more. So in general, a bipartite graph might look like this. So you have maybe n candidates on the left, n candidates on the right, and you have some preferences which are indicated by all these lines going between these sets of vertices. Yes. Okay. All right. So all right. So now what I want to do is I want to know if there is a way of assigning each candidate a distinct job, right, in their list of jobs that they want to do. Okay. So can this be done? So how would you go about finding this out, right? Well, if you think about this problem, there's one sort of simple strategy that comes to mind. And the simple strategy is to just try all possible combinations, right? So for example, I have this candidate U1 over here. U1, there are n possible jobs that U1 could be assigned. So just try all n combinations. Okay, so U1 has n possibilities. So for example, the first possibility is V1, which U1 is not interested in, but then there are other possibilities. So just try possibilities one after another. And once U1 has been assigned a job, try all the possibilities for U2. Okay, once U1 has been assigned a job, that's one job out of the picture. So U2 has n-1 possibilities, try all of those. Then U3 has n-2 possibilities, try all of those, etc., etc. At some point, if you get stuck and you can't assign a candidate any job, then maybe you have to stop and restart. Okay, try other possibilities. So the simplest strategy in this situation is to just try all possible combinations. Okay. But the only problem is that the number of possible combinations is incredibly large. Okay, incredibly large. Okay, so how many combinations are there? So the number of possibilities is n into n-1 into n-2 all the way down to 1. Okay, and that's a number called n. That's a kind of a function of n called n factorial, which you've possibly seen in combinatorics and other things. Okay, so it's the product of all numbers from 1 to n. And it's actually impossible to easily describe how fast this number grows. Okay, but just to give you an idea, suppose I take n equals 100. Okay, 100, for n equals 100, this number 100 factorial is greater than a number of particles in the observable universe. Okay, so total number of particles in the observable universe, something like 10 power 90 or something, and this is more than that. Okay, so if you're going to try all possible combinations, there's no way you're going to be able to solve this problem in any reasonable amount of time. Okay, so that's not a feasible strategy to do this. Okay, so in order to be able to solve this problem, we actually need to come up with a kind of a more clever, refined strategy. Okay, and I want to describe to you now kind of an algebraic approach towards solving these problems that uses this fact about polynomials that we've seen in a nice way. Okay, so I'm going to go ahead and do that. Okay, so now let's see. So it's going to be an algebraic approach. The advantage of this approach is going to be much faster than trying all combinations, much, much faster. So fast that you can actually do it in your computer in a couple of minutes or maybe even seconds. Okay, and but there'll be a disadvantage. The disadvantage is that this strategy that I'll describe will not always be correct. Maybe correct 90% of the time, but there's going to be some chance of error. Okay, so it's kind of what is called a randomized strategy. So it uses random bits on your computer, but is right 90% of the time. Okay, all right. So what is this strategy? It uses fanciful polynomials in a nice way. So let's go ahead and see it. So the idea is the following. So you have, again, a list of candidates, a list of jobs and their preferences. Okay, and what we are going to do is translate this into a polynomial. Okay, what kind of polynomial? Well, we've seen this polynomial on the kind of the first slide of this talk. It's the determinant polynomial. Okay, so let me just say a little bit about this polynomial here, and then we can see the application. So what's the determinant polynomial? Okay, so whenever you have a square matrix, in this case, it's a 3 by 3 matrix, the determinant is a polynomial in the entries of the matrix. Okay, so what kind of polynomial is it? Well, what I want to do in order to get a term in this determinant polynomial is I want to choose one entry from each row and each column in this matrix. Okay, so for example, if I choose the first entry in the first row, the second entry in the second row, and the third entry in the third row, then I get this monomial x1, x5, x9. That's in the determinant. Okay, similarly, I could choose x2, x6, x7. That's here, and so on. Okay, I don't have terms of the form x1, x4, x7. That's because I'm not choosing anything from the second row or the third row. So I have to choose a distinct entry from each row and column. Okay, exactly one entry per row, one entry per column, and all the terms that I can get that way, those are the terms in the determinant. Okay, there are also some signs here, but let's not worry about the signs for now. So this is essentially the determinant. So I have to choose exactly one entry per row and column. Okay, that's roughly the determinant. And so now how am I going to translate my problem into the determinant? Well, what I do is I'll take this determinant. So I have this graph here, this candidates and jobs, and I'm going to take a determinant closely related to this configuration. Okay, so what will I do? Well, I'm going to take exactly the determinant that I've written on the left-hand side, okay, all distinct variables, except that, so the rows of this matrix are sort of, I think of as related to the candidates. The columns of this matrix I kind of think of as related to the jobs. And whenever a candidate does not want a job, right, I zero out that entry. Okay, so for instance here, U1 does not want the job V1, so that corresponding entry is zeroed out. U3 does not want the job V2, so that corresponding entry is zeroed out, etc. But if U3 wants V3, then I leave it as it is and I have a variable in that entry. Okay, so what I've done is I've defined a matrix based on my candidates and jobs. And now what I'm going to do is I'm going to look at the determinant of this matrix. Okay, all right. So what happens when we take the determinant of this matrix? Again, as I said, the terms of the determinant correspond to taking exactly one entry in each row and column. Okay, one entry in each row and column. That means in the first row, I'm going to take one among these entries. Okay, and that sort of corresponds to assigning to candidate U1 one job. Okay, it's exactly the same thing, right? Because this row corresponds to U1 and I have 3 jobs. So it's corresponding to assigning the candidate U1 one job. I take one entry here. And similarly, I take one entry from this row that corresponds to assigning candidate U2 one job. And similarly for the candidate U3. Okay, so this condition of taking exactly one variable from each row and column, it exactly corresponds to assigning each candidate a distinct job. Okay, so that's exactly the same thing. Okay, so the determinant exactly corresponds, the terms in the determinant correspond exactly to assigning the n distinct candidates n distinct jobs. Okay, so that's exactly what we want to do. But there's one more condition, right? We have to only assign candidates jobs that they want. Yeah, and that's where the zeros come in. Because every time we take a term where, for example, U1 is assigned job V1, then that corresponding term is going to be 0 because I put a 0 here. Okay, so since I put a 0, the only terms of the determinant that survive correspond to assignments of candidates to jobs where each candidate gets exactly one job and each candidate only gets a job that they want. They don't get a job that they don't want. Okay. So if you expand out the determinant in this situation, you can see that what you get is x2, x4, x9 with a minus sign. And that exactly corresponds to giving u1 job v2, giving u2 job v1, and giving u3 job v3, which is a valid assignment of candidates to jobs. Okay, so that's the setup. So what did we do? We started with this combinatorial problem of the perfect matching problem, and we turned that into a polynomial problem. Okay, and what's the feature of this problem? This feature of this problem is that the determinant in this case is going to be exactly the sum over all those valid assignments of assigning candidates to jobs that they like. Okay, and what I want to know is there even one such assignment? Is there even one way of assigning candidates to jobs that they like so that every candidate gets one job, right? And that's exactly the problem of checking if the determinant is non-zero. The determinant of this matrix is non-zero. Okay, so let me just state that in slightly more formal language. So there's nothing special about n equals 3 here. This is true for arbitrary n. So given any bipartite graph with n vertices on each side, so n candidates and n jobs, we can define an n by n matrix in this way. The entries of this matrix are either going to be variables like this or zeros. Zeros correspond to when candidates don't want those jobs. And the determinant of m is non-zero exactly when this graph has a perfect match. Okay, so exactly when the graph is a perfect matching, you're going to get a term like this. If there is in fact no way of assigning candidates to jobs in a correct way, then this determinant itself will be zero. Okay. All right, so this is actually quite a bit of a mouthful. So if there are any questions about this, I'm happy to take them.
Sir, what is the proof of the process and why does this process contain some error sometimes?
Right, so I've not yet told you the process. I have to tell you how to check if the determinant is non-zero, right? In this case, the proof that, so I'm guessing you're asking the proof of this last fact here. The determinant is non-zero exactly when the graph has a perfect matching. I'm guessing is that correct?
Yes, sir. And even if the determinant is non-zero, suppose we have certain a polynomial term of two. I mean, suppose x1, x2, x3 minus x2, x4, x9. If such a case arises, then what will happen?
Right. So the determinant polynomial in general could have many terms. And now the question is how to check if it has some terms, right? So what we want to know is there even one, let's say one valid assignment that's equivalent to checking if the determinant is zero or not. And now how do we check that is sort of something I'm yet to describe. But for now, let's just agree on the fact that the determinant polynomial could be zero, right? It could be zero, but it's going to be non-zero exactly when the graph has a perfect match.
Sir.
Yes.
Sir, if u1 isn't assigned to v2, then what would be the problem? Means if x2 is 0.
If x2 is 0, you're saying?
Yes.
If x2 is 0, you can see that the determinant vanishes, right?
Yes, then what would be the problem in the graph?
What would be the problem in the graph? So let me try to understand that. See, in the graph, as I've said it currently, oh, I see. You're asking what would be the problem in the graph. Well, what would happen in the graph is that you can see that both u1 and u3 only want the job v3.
You want, all right.
Yeah, but they can't both be assigned that, right? If they're both assigned that, then all the jobs can't get done. Since there are n jobs and n candidates, each candidate has to get a distinct job.
All right. Got it.
Yeah. Good. Okay, great. So, all right. So what has happened so far? Okay. So we turned this kind of problem of checking if the graph has a perfect matching into a different problem. What is that different problem? The problem of checking if this determinant is non-zero. Okay, this determinant is this big matrix. So think of n as 100 or something. So it's a 100 by 100 matrix. It's got variables and zeros in it. And I want to check that if I expand it out, will I get the zero polynomial or not? Will any term survive? And that's sort of the question that I want to answer. Is the determinant non-zero? Okay. Yeah, and so now, how do you check if the determinant is non-zero? Well, you could just expand, right? I told you what all the terms in the determinant are. You have to take exactly one term from each row and column. So look at every way of taking one term from each row and column, multiplying it out. Okay, but if you do this, then you can see that again, this is essentially the same thing as trying all possibilities for the matching in the graph. It's like, oh, the first row can take n options, the second row can take n minus 1 options, etc., etc. So you will again end up taking n factorial many steps to do this. And again, that's a prohibitively large number. That's very, very big. So you don't want to do that. Okay. All right. But here's where a second fact about the determinant enters the picture. The second sort of magical fact. Okay. And the second magical fact about the determinant is something the Chinese knew more than 2000 years ago. Right? And this was essentially that you can evaluate determinants quickly, where if instead of variables here, you actually have numbers. Okay, so here instead of x2, xn plus 1, xn plus 2, etc., I actually have numbers like 2, 3, 4, 5, minus 1, whatever. Then the determinant of this matrix is a number, and actually I can evaluate that number quickly. Okay, so that can be done really, really fast. Okay. And how to do this? Well, this is an algorithm that I spoke about some time ago. It's called Gaussian elimination. So if you're an undergraduate student, you've probably seen it in your basic linear algebra course. I don't know if one sees it in 11th and 12th these days. But the Gaussian elimination is this very nice algorithm, which in particular allows you to compute the determinant of a numerical matrix. Okay, so if you have a matrix of numbers, then in something like n cubed steps, so it's an n by n matrix, so something like n cubed steps, you can actually compute the determinant. Okay, so how big is n cubed? Well, if I take off n as 100, n cubed is something like 10 power 6. It's about 1 million. Okay, just compare this to 100 factorial. I told you 100 factorial is more than 10 power 90. Okay, it's more than the number of particles in the observable universe. But n power 3 is just 1 million in this case, right? And 1 million operations is something your computer can do in a fraction of a second. Okay, so the Gaussian elimination algorithm is really very efficient, and for reasonably large matrices, you can actually compute the determinant quickly. Okay, so just a final setup. So how do we use this in order to solve the problem? I want to check if this determinant is non-zero. The matrix unfortunately involves variables. If the matrix didn't involve variables but just involved numbers, then actually I can compute the determinant fairly quickly. But currently the matrix involves variables. So how do I kind of get around this fact? This is where the lemma about polynomials we saw a few slides ago comes in. Okay, a non-zero polynomial evaluates to a non-zero value on most points in a big grid. Right, we saw this some time ago, and that's where this is where we're going to plug that fact in. Okay, so here I have a non-zero polynomial. I want to check if the polynomial is non-zero or not, but I have a potentially non-zero polynomial. It's a polynomial in up to n squared variables, right? There's an n by n matrix, so up to n squared variables. It's a polynomial of degree n, right? Because I take exactly one element per row and column. Okay, and I want to check if it's a non-zero polynomial or not. So how am I going to do this? I'm just going to evaluate it at a random point in a big grid. Okay, so I take a really big grid. This capital N is going to be much larger than the degree of the polynomial. Okay, and I'll just evaluate it at a random point there. Okay, and somebody was asking, where is the error going to come in? And this is where you will see it happening. Okay, so let's look at what happens. So if the determinant of M is the zero polynomial, right? If the determinant of this matrix is a zero polynomial, it doesn't matter where I evaluate this polynomial, I'll always get 0. Okay, so if the determinant of the matrix is a zero polynomial, every point of the grid, the polynomial vanishes, is a root, so I'll always get 0. Okay, on the other hand, if the determinant is a non-zero polynomial, okay, so there is a matching in the graph, and therefore the determinant is a non-zero polynomial, yeah, then it cannot vanish everywhere on the grid, right? In fact, it vanishes at very, very few points on the grid. That's what we saw, right? But we could be unlucky when we pick a random point from the grid. We could be unlucky and we could pick one of the few points that actually roots of this polynomial. Okay, and if we are unlucky, then we'll actually end up being fooled. We'll actually end up thinking the polynomial is a zero polynomial. But if we are not unlucky, if we are reasonably lucky, then we'll end up seeing that this polynomial is actually non-zero. Okay, so if the determinant is 0, then the polynomial always evaluates to 0. If the determinant is non-zero, then there is a small chance of failure. And this is where the chance of failure comes in. The chance of failure is the number of roots, which we saw some time ago, divided by the total number of points in the grid, which is this number here. And so if you sort of just take the ratio, you can see that the chance of that we get unlucky and that the non-zero polynomial vanishes at a random point in the grid is this degree of this polynomial, which is little n, by capital N, which is the size of the grid. Okay, and now you can make this number as small as you want. Okay, you take your capital N to be a really big number, then you can make this number as small as you want. It's completely in your hands because the grid that you define is completely in your hands. So you choose your grid to be really big, then you can make this chance of finding a root very small. So a non-zero polynomial then evaluates to a non-zero value at most points of the grid, and therefore you'll be able to tell the polynomial is non-zero or not just by evaluation. Okay, so this is kind of a whirlwind tour of an algorithmic application. So let me just do a quick summary of it, and I'll take some more questions after that if there are any. Okay. All right, so quick summary of what we just saw. So we started off with this problem of checking if a graph is a perfect matching, and we reduced it to checking if a polynomial is non-zero. Okay, so this determinant-based polynomial is zero or not. Yeah. We got lucky in one sense is that we have this ancient algorithm for evaluating determinants of numerical matrices quickly, the Gaussian elimination algorithm, which is a really amazing algorithm. Okay. But finally, in order to check if the determinant polynomial is non-zero, we had to turn this variable matrix into a numerical matrix. And the way we did that is that we just substituted values from random values from this very big grid. And we used the fact that at a random point in a large grid, a non-zero polynomial is very unlikely to vanish. Okay. In fact, the chance that it vanishes is some parameter based on the degree of the polynomial and the size of the grid, and we can make that as small as we want. Okay, so we can reduce the error of this by increasing the grid size. Okay, so that's more or less the summary of this algorithm. So I had one more application in mind, but I think I'm sort of I've spoken quite a bit and rambled on for much longer than I anticipated. So what I'm going to do is I'm going to kind of skip ahead this one last application and go to the summary slide. Okay, but this is actually a nice application to Combinatorics, and I'll probably share my slides, and if the organizers want to share it with people who are interested, then you're welcome to take a look at it. Let me just skip this small application. Okay, and let me just summarize. Okay, so what's the kind of overarching theme that we addressed in this talk, and what should you take home? Well, throughout this talk, we've sort of based it around applications of a simple mathematical question. And the mathematical question is, how many roots can a non-zero degree D polynomial have? Okay, so we saw the univariate version of this question, which is kind of more or less high school stuff. And we saw a nice application of that in coding theory. We also saw the multivariable question and how that has been, the answer to that has been found independently by many mathematicians over the years. Okay, and even these very simple facts about polynomials have real-world applications and mathematical applications in many areas. So we saw an application in coding theory, another one in algorithm design for the perfect matching problem. There's also an application in combinatorics that I didn't get time to go through, but this is all barely scratching the surface of what's known. Okay, there are millions and millions of such things. So the questions about polynomials that sort of arise from these applications, and in turn, this sort of gives back to mathematics new questions and new areas of investigation. So I invite you to kind of take any one of these things and go deeper into it and try to understand how polynomials and algebra in general is useful in many areas of mathematics and computer science. Okay, so that's all I had to say. Thank you.
Thank you, Professor. It was a really wonderful talk, how you started from some simple polynomials and then showed how can we connect it to TOC and the Gaussian elimination, and like everything was covered in just one talk. It was really wonderful, and you managed to keep the attention of students also till the very end. So that was really wonderful. Thank you for your talk. So we will now take up some questions. So if people have any questions, they can either put it in the chat box or they can also unmute themselves and ask directly to the professor. And if you have any other questions after the talk, then you can also mail us and we will get it replied by the professor.
Sir, I have a question.
Yes, please.
So in the perfect matching problem, we were trying to understand if there is a solution. But what if we want to find a solution, exact solution, then it still takes n factorial steps, right? So there's no better algorithm for it.
It's a beautiful question again. So you can actually find a solution as well. So only it will take a little bit more time. It won't take n factorial time. So you can imagine that if there is a solution, right, there has to be a solution in which the first candidate gets one of the first n jobs, right? So you just try the first n jobs for the first candidate. So you just try, okay, give the candidate job 1, give the candidate job 2. And every time you give the first candidate some job, you will be able to check if the remainder of the candidates can be given jobs consistent with this assignment, right? Let's say you give the first candidate job 1, then what you're left with is an n-1 plus n-1 vertex graph. And then in that graph, you can check if there is an assignment to the remaining candidates or not. And let's say there is, then now you can give the first candidate the first job, and then you can just do the same procedure on the remainder of the graph. Okay. And so in something like n iterations of this basic algorithm, you can actually find the job of the first candidate. But then you'll have to repeat that again n times to find jobs for all the candidates. So overall, this will take something like n to the 5 steps instead of the n cubed steps that I spoke about some time ago. But you can significantly speed this up by being cleverer than this. But already this is much better than n factorial. Okay.
So what if we started out with all the people that only want one particular job, and then we assign them all? Then we see the people who wanted 2 jobs and what is left, and we repeat that same process of giving exactly one job which is left.
Yeah, unfortunately, all of those get into. So you can try. It's a very good strategy, but such strategy. So these are called these are called in computer science. These are called greedy strategies. Yeah, it's not a kind of a mathematically formally defined term, but it is. So, but these greedy strategies for a perfect matching problem typically don't end up working. You'll get stuck. There will be certain situations in which you need to assign candidates who have more jobs for some reason first before you assign the ones that require fewer jobs. Yeah, but you should try to come up with examples. It's a great question and great thing to try.
Sir, we can certainly assure that for very large grid that the polynomial will eventually get a point where it will not vanish for the case with non-zero determinant, because if we fix all the n for the n-dimensional case, m-dimensional case, all the m-1 dimension we are fixing, and we are getting a polynomial in 1 dimension. So that's by the fundamental theorem of algebra. After with the degree, say that variable has degree n, so greater than n cases we are having that. So it is a finite. After a large enough grid, we are getting that non-zero.
It's a very good idea. The only problem with what you're saying is that when you fix the first m-1 variables, how do you ensure that the polynomial does not vanish? Right? It might become the 0 polynomial. So you just have to ensure that, and that's essentially what the proof does, right? So you want to keep setting variables. Of course, it may end up, if you end up with one variable and it's a non-zero polynomial, then you're fine, as you said, but you may end up with a 0 polynomial, right? So you have to ensure that doesn't happen. And that's essentially what the proof is doing. Okay,
sir, thank you.
Sir, there is a question in the chat box. Can we use polynomials to effectively compute chromatic number of a large graph?
So this here I'm actually a little bit. I think maybe the question is about these graph polynomials and other things. So the short answer is no. Okay, so the chromatic number of a large graph is suspected to be very, very hard to compute. Okay, so there is always a simple strategy of the form that we describe for matchings. Try all possible combinations. And it's suspected that there is no faster method of finding the chromatic number of a graph. So the short answer is there is no known technique of using polynomials to be able to effectively compute the chromatic number of a graph. That doesn't mean there isn't, but it's suspected by most people that there isn't any method based on polynomials, not based on polynomials, nothing. There's no efficient method of finding the chromatic number of the graph. So it's not known so far, but yeah.
Okay, thank you. So that was. So if there aren't any other questions, okay, so there is another question. So can we check for 0 eigenvalues in the stable matching problem, and can that help us in solving the problem?
In the perfect matching problems, 0 eigenvalues, you say? I'm not entirely sure. So okay. So let me just see if I can answer this question. So typically, what is being asked is actually a very it's an insightful question. Is to, if you take the matrix, there's a natural matrix corresponding to the graph that we saw, and if you look at the eigenvalues of that matrix, does that give you information about the graph? Typically, yes. Okay, but so the matrix that we were looking at, the matrices that we are looking at are not symmetric matrices. They don't have any nice structure. So it's not entirely clear. There need not be many eigenvalues. There might be, of course, there will be one eigenvalue. It need not be real. So it's hard to be able to get a lot of graph theoretic structure from that information. My feeling is no, but I cannot be sure about this, because there are many instances of where eigenvalue based ideas are useful for graph theoretic problems, but I don't know in this context. So that's my best answer, unfortunately.
No, that was fine. That. So I think we can come to a conclusion now. So if you have any other question, then feel free to mail us, and we will take up with the professor afterwards and then get it replied. So thank you, sir. It was really nice, and it was an amazing talk how you started from like simple polynomials and showed us various applications. And we never knew that like we can use it in several other ways, and like that, and also in coding theory. That was really amazing. So thank you once again for your amazing talk, and thank you for accepting our invitation.
Thanks very much for inviting me. Yeah, thank you.
So tomorrow we will have our last day of the camp, and the first talk of tomorrow's will be by Professor Jayakumar Radhakrishnan, who will talk on how entropy can be used in several places, and it can be used to get communications and everything. So hope to see you all there, and thank you once again for joining us today. Thank you.
Thank you very much, sir.
Thank you.